Hi, my name is John Straube, and I'm a principal at RDH Building Science. Today we're going to have an introductory video that we're entitling Building the Perfect Wall. And while I say it's introductory, actually the concepts are actually profound enough and significant enough that they have meaning to people who are just entering the industry, as well as people who have been practicing for 30 years or more. And that's because there's been a lot of important changes in how we build our building enclosures and what we expect of them. And this bears a re-examination. And that's what we'll be doing for the next about 60 minutes. So we're going to start with talking about what are building enclosures, and then discuss what it takes to get to a high-performance building enclosure and some of the other issues that are influencing modern design. We're also going to look at membranes and layers in enclosure systems, particularly walls, as an example of the entire enclosure. And then talk about what it takes to move forward and implement these ideas in practical building design. So one of the reasons that changes have been occurring is that people are looking for more than just basic performance that meets the code. We're having higher and higher demands for durability, low maintenance buildings. We want better energy performance or lower energy or carbon emissions because of energy use. We want to have improved comfort. Our occupants today really have high expectations at being able to be thermally comfortable, moisture comfortable, acoustically comfortable. We also have an expectation that our buildings can manage things like mold and pollutant transfer through the building enclosure that can impact the health of the occupants. And we also now have even added stuff to this list like resilience, the ability to survive when power outages occur, flooding, wildfires, etc. And how do our buildings survive these significant but usually relatively temporary disruptions to the world around us? So the way that we've had to deal with these types of increasing demands on our occupancy and on by the building code regulations, etc., is that we've started to add layers and new materials to our building enclosures. And as a consequence, we've started to get very complex assemblies. Often there's many more layers, there's many more different choices for our assemblies. There are different types of materials available. In 1925, if you were building City Hall, the materials that you had available, the number of layers and the number of assemblies could all be counted on one hand. And today, we have so many choices. And of course, then you add to that more and more demanding regulatory constraints for life safety, environmental performance, and we've added many consultants to help us pass through these many more obstacles to getting the building built. And so a big challenge, perhaps the biggest challenge in today's building design, is managing complexity, finding a clear path that connects the design idea, the client's needs, through all of these many complexities that have just slowly accreted in the last 50 or 75 years. So the way we're going to start this is we're going to break down our building into components. And so we're going to try and manage this incredible complexity by breaking it apart into understandable pieces. So the first chunks we're going to break apart are the four pieces of a building. That's the primary structure or superstructure. Then we have also the service systems such as lighting, plumbing, communications, ventilation, elevators, escalators, fire suppression. Then we have the fabric of the building such as interior partitions, furniture, suspended ceilings. And finally, the real focus of this seminar, which is the building enclosure, which is the layer that wraps around the outside of the building and separates the indoors from the outdoors. So the enclosure has become a real focus in many modern design thinking. And certainly when one goes to trade shows, you see a lot more emphasis on the building enclosure. There's a number of reasons for that. Is that if we get the enclosure right, it makes things like heating, ventilating, air conditioning, and lighting way easier. But if we also don't get the enclosure right, we have a lot of maintenance problems and repair problems. The enclosure is at the core of many complaints about lack of durability and the need for higher maintenance. And so really thinking about the enclosure and what we want it to do is important to clarifying our world and how we get to a more simple, straightforward solution. So just a quick review, be clear that the role of the building enclosure is that of an environmental separator. And the environment that it separates is the indoors and the outdoors. Interior partitions can also be environmental separators between, say, a swimming pool and a hotel lobby. But that's not an enclosure. The enclosure is very specifically that separator between the outdoors and the indoors. And so all the parts that make up walls, windows, roofs, floor slabs, glass, etc., all of that is the enclosure, and it must be all knitted together to make it a properly performing enclosure. So when we are looking at the enclosure, we are trying to put it in the context of recognizing that it's not the only thing that separates the inside from the outside. On a warm, humid day, it's not often enough to just have a really good enclosure. You also have to remove the heat generated inside of a building with an HVAC system. I might have a very good building enclosure that has a great air barrier, but that doesn't relieve the need. In fact, it enhances it to provide good ventilation. And at night, it doesn't matter how good of a job I do on the glazed portion of my building enclosure, I still need an electrical lighting system. So the building enclosure fits in there as part of an overall strategy of how do I meet the internal occupants' needs. Of course, we use mechanical systems for those parts that we can't meet by the passive building enclosure, but we can also site the building in a way that minimizes the load of, say, wind loads, solar loads, etc., so that the role of the building enclosure is a little easier to achieve. So the enclosure itself, we can now break down further. There are three big categories of functions that the building enclosure has to meet. Number one is, of course, support. The fundamental thing is it has to be able to support its own weight. It shouldn't be falling over because of wind loads, because people push on it, etc. It's different than the support of the entire building structure, because the building structure usually simply collects the loads from the enclosure and the occupancy and delivers them to the ground. Whereas the enclosure may only collect a relatively modest floor-by-floor area, deliver that to the primary structure, which carries it to ground. The control layers is something we're going to focus on. And the controls categories are all about why we build the building enclosure. To control the flow of matter and energy across that enclosure is necessary if you are going to separate the indoor environment from the outdoor environment. The final one, of course, is finish. And this is not a technical function. It is a requirement of the building enclosure for human use and occupancy. So we're trying to make sure that the people who are looking at the inside of the enclosure are happy with that painted drywall or the flowers on the vinyl wallpaper. And we're making sure that the people on the outside are happy looking at that brick facade, that metal panel facade, that stucco facade. There are other things going on in the building that sometimes influence the building enclosure. And the one I'm going to point out here is distribution. It is not the job of the building enclosure to distribute electrical wiring. It's the job of the building to do that. However, sometimes the electrical wiring, and heaven forbid the plumbing, has to go through the building enclosure. And in that case, it can be something that takes a serious amount of effort to make sure that there are no compromises to the performance of the support, the control, and the finish functions of the enclosure. So when I mean support, I not just mean wind loads, we also mean earthquake loads. We often mean needed to resist shrinkage, expansion, and contraction of the materials that make it up. That's what we call these rheological loads. We have to think about abrasion and impact. Structural engineers don't actually design things for those particularly. We have to consider that in the use case. If it's a primary school schoolyard, for kids at recess, you need something that can take a lot of abuse. Those aren't structural loads, but they really matter to the designer of an enclosure. When we move to the control side, we actually know that pretty much in practice, the number one control layer we have to care about is the rain control layer, and that'll be mentioned several times throughout the seminar to re-emphasize that. But the second most important one that many people are just now starting to practice is a good air barrier, a continuous layer that resists the interchange of air from outdoors to indoors. Then we have also the heat flow control, and finally vapor control. Now, those are not the only 4 control layers. Those are the 4 we're going to focus on because in practice, they're often the most important. And this is the order of importance. Rain is number 1, air is number 2, and vapor is number 4. So we don't always want a vapor barrier. Many times we explicitly want to avoid a vapor barrier. But we do always want a rain control layer and an air control layer. So other types of control layers other than those 4 include things like acoustic control layers, fire control layers, smoke, light, etc. And those can be quite important on certain types of building enclosures. So not to be forgotten. But those ones I've listed earlier, the rain, air, heat, and vapor, exist in almost every practical building enclosure from a simple strip mall to a high-end museum. So then we have the finish, and the finish, as you can see, is mostly inside, outside, because that's what people see. And the finish doesn't have to be everywhere, because above suspended ceilings, across structural floor systems, for example, behind structural walls, you don't need to put a finish on the inside of that enclosure. It's only where people can actually see it. So in the old days, we would make buildings as you see in the upper right here. And this is a very simple building. It's about 1,200 years old. It's an Irish church. And the reason I use this as an example is that there are basically only rocks in this entire building. There's one building material, one trade went from footing to the ridge of that building. That was a simple world. But when we asked the question, what did rain control? The answer was obviously the rocks. If you ask the air control, well, it was the rocks. It didn't do a very good job of them. What did the thermal control? The rocks, and it didn't do a very good job of them. So that's one of the things that we have said, well, we're making modern enclosures with higher expectations for comfort, for energy, and therefore we've started adding layers and systems to the building enclosure. And today, a building might start looking like the bottom right, where we have the primary structural system, reinforced concrete in this case, completely divorced from the enclosure support system, a light gauge steel stud. 2 separate structural designers. One does the steel stud, one does the reinforced concrete. 2 separate trades. And that's just the support side. And then we move to, well, what's doing the air control? Maybe it could be the white polymeric house wrap that we see here, except that that house wrap doesn't have any tape, and so the designer hasn't included it, so they don't really get an air barrier. As a water barrier, that could work as long as it's overlapped. The brick, you can see in the very bottom corner here of that figure, is not there to stop water or air. It is a finish, which may also be good at dealing with impact and abrasion. So that might be a reason someone chose it. So now we have multiple layers, multiple trades, multiple consultants worrying about things like fire, sound, air separately. And so it's become really difficult to coordinate that whole team, particularly when there's no clarity in the words they use to describe the function or the objectives of their work or their product. So this diagram here is trying to just demonstrate how we've gone from relatively simple one trade or 2, one material or 2 in building enclosure systems to multi-trade, multi-layer systems. So the core thrust of this seminar, therefore, is to say, let's clear up these uncertainties, make sure we all use the same language when communicating with our trades, with our inspectors, with our product suppliers, etc. This diagram here is actually from, it says page 6. And so when you see that orange page 6 listed there, what that means is from a guide I wrote about, a technical guide for the selection and installation of Vent SA, a self-adhered vapor permeable membrane. And the context here is important. We're not too worried what you use for your support structure. Could be concrete, could be steel stud, could be mass timber, could be a whole bunch of things. But from the building enclosure performance point of view, we are very concerned about seeing those 4 layers. Now those 4 layers don't always have to be independent materials, but every functional building enclosure design needs to be able to identify what is doing the water control, what is doing the air control, what is doing vapor control, what is doing thermal control. And of course, what's the exterior finish, what's the interior finish. And in design, we also have to make sure we know how are we going to run wires through these enclosure walls or roofs, because they're commonly needed. Now, if you're not doing them, maybe you're surface mounting, but you have to have an answer for how that happens. So we call this the perfect wall because it includes all of the components that we know we need and clearly identifies them. Now, the arrangement of all of these layers is quite carefully selected. This set of drawings here is an arrangement that works for all normal human occupancies, from swimming pools to classrooms to residences to museums, in all climates, whether we're talking about the far northern reaches of a tundra with blowing snow, or we're talking about deserts, or we're on the Gulf Coast of the Gulf of Mexico where we have lots of heat and humidity. It works in all of those. So that's another reason we call this a perfect wall. But probably many of you will notice that we don't build many walls like this. And that's because if you reorganize the materials, if you have unique material layer properties, you can often make changes to this assembly to have it work as good as a perfect wall. But you have to know what those things are, and we're going to be talking about that. So this is even a simpler version of the perfect wall, and you can see what's changed in this design is that we have collapsed the vapor, water, and air layers into one black line. And we have the structural support on the inside. We haven't talked about any interior finish. We have the insulation layer on the outside, and we have a cladding on the outside of that. So that's the simplest thing. Now, when it comes to high performance enclosures, we have to be a little bit more precise about what we mean other than just saying we have a rain control, we have a thermal control. We have to start talking about the quality of performance that those control layers can deliver. And one more thing, which is going to be important. So to start with, a high performance enclosure provides a high level of control of heat, air, water, fire, sound, of course. But the biggest limitation to performance is not that the layer isn't of a good quality, it's because we have holes in that layer. And so when we're worrying about air tightness, the most likely cause of poor air tightness performance of a building is not that that air barrier material is letting air through, but that there is a crack between 2 adjoining air barrier components. The biggest reason we have leaks, of course, is not because water is coming through our water control layer or our house wrap or our building paper. It's mostly because there's a discontinuity, a joint, a penetration, an opening. And so the key issue in terms of getting high performance enclosures is continuity above all. Make sure that those heat, air, water, vapor, thermal layers are actually all have no holes in them. The next thing beyond that is now you need to choose materials that will, without holes, perform up to the level that's expected for your wall, your roof, or your foundation. So, taking that concept of the perfect wall, and you take this and now you tilt it on its face, and that gives us the perfect slab. And so in this case, it means that the structure's on the inside, just like it is for the wall. There's a membrane below that structural slab, which is air, water, and vapor tight. And then below that, we have some thermal control layer, often some sort of insulation material. There is no exterior finish because there's nobody below the slab to enjoy that finish. But there is often a topside finish, and that means you have to add that to the design. If I take the perfect wall and tip it on its back, I get the perfect roof. Structure is again on the inside, protected from the environment, and then on top of that structure is the air, water, and vapor control layers, and then on top of that is insulation, and then some sort of a finish. So that is what I just described for the perfect roof is the inverted roof, or protected membrane roof, which is a more technically correct description. So that type of a roof is widely used for high-performance building enclosures that have high durability expectations, but still 90% of commercial roofs and probably 100% of residential single-family roofs don't build like that. They reorganize the layers for various economies and simplicities, and so you have to be careful about now how you design those things. So here's an image of that roof. Protected membrane, as it said, because the membrane is protected from the things that cause it to fail. Ultraviolet radiation, high temperatures, low temperatures, and people walking on the roof to do service. And for all of those types of things that cause membranes to fail, this membrane is protected by its insulation layer. The insulation layer is protected by the stone layer or paver layer or plaza decking layer on top. And then underneath, of course, is the roof structure, and the roof structure is now kept always at constant temperatures, year in, year out, never sees moisture, ultraviolet radiation, high or low temperatures, and therefore that can be made out of many, many materials, and it will remain durable for centuries, literally. So the floor slab, as I described, concrete slab is common on top, doesn't have to be concrete. But there does need to be a control layer that separates air, water, and vapor under that slab. Then we add thermal control in climates where this makes sense, which is many cold climates. And then on top of that, below that, we have stones, and those stones are there for a couple of reasons. One is to level out the earth from the excavator so it's flat enough. And the other is it provides a path for water to run so that any groundwater can be drained away before it gets to the insulation and the control layers. So we take these concepts and we're going to apply them to this beautiful building I have right here. And so obviously the wall, pretty straightforward, cladding, airspace, insulation, membrane, structure. Put it on the roof, put it on the floor slabs, and you'd think, well, that's how you build the perfect building. Well, maybe, but the real challenge comes when how we connect the actual roof to the wall. That's where we have a lot of problems. And then also where the floor slab is connected to the wall below grade, the footing. And then really where we have a lot of problems is the fact that we put windows into this building enclosure, and trying to connect all of these layers together, the air, heat, and vapor, at these transitions is a major part of the construction document stage. It's a major concern during the build for people to do inspections, because that's where failures occur. That's where we know we have poorer performance and where people get dissatisfied. It's pretty rare in the body of the wall or the roof to have significant problems. So one of the other interesting problems here is that this is not just a technical issue of designing materials in the right arrangement or even drawing this. You also have to give some thought to who is going to build it. So this is classically the case where the roof meets the wall, because the roof is done by a totally separate trade than the wall in almost all cases. And hence that transition, it's not just what materials go together, but who's responsible for making the final closure so you don't have a hole. It's the holes where we're going to have failure, and how do we avoid that? It's not just to draw the layers, it's to give some thought to a reasonable construction sequence that allows the layers to be made in a water, air, and thermally tight manner. So if you build a building like this, you've definitely created a lot of work for yourself, because all of those three-dimensional details, all of those roofs meeting walls, all of those corners and window penetrations require someone to design how do we make the heat control connect to the heat control, the water to the water, the air to the air, the vapor to the vapor, the structure to the structure. And because there are so many details, it takes a lot of design time and a lot of coordination. And sometimes people don't spend enough design time or don't do enough coordination, and a complex building like that will routinely have performance problems and will routinely cost more money. And I think most people know that. So just as a reminder, in normal building projects, we have this image here on the right, which we use as an example of many of the details we find in common modern buildings. We need to have a detailed drawing that shows how water continuity will be maintained, air continuity will be maintained, thermal continuity is managed, and vapor continuity is managed at every one of these red circles. And those red circles are simply practical points where there's either a change in plane as we go around a corner, a change in material as we go from, say, a stucco wall to a brick wall, or from precast to curtain wall, or a change in trade, going from a roofer to a brick mason. And wherever we have those changes, we've tried to indicate with a red dot. And this helps us in the initial review stages because you can't just look at the drawings that are in front of you to say, did they provide a heat flow control layer, and did they make it continuous through all the details? You also have to ask, did they draw all the details that are necessary for this building? And so that's when you have to look up from the drawing set, think about the building in 3 dimensions, and ask, so which details exist in this building but aren't in the drawing set that I'm currently reviewing? So to get to high performance, we've already said high levels of control, not have a lot of holes in it. But to get to that, we need to have good rain control, good air control, good thermal control. And from energy point of view, we have to separate out solar control from temperature. So we actually have to deal with things like shade instead of just insulation. And we make this continuous across all transitions, penetrations, and joints so that we can say we have continuity and the materials can do their job. So when we look at the moisture side of the building problem, obviously this shows up in the rain control side heavily. It's the #1 concern. Condensation is the second most important one. And then we also need to provide some drying. And so we're going to look at how we can use membranes to achieve all of these things. So when it comes to rain control, it's important to realize that there are 3 fundamental approaches to rain control. And this has been scientifically worked out to say there are exactly 3. Many people in a modern world look at the drain or so-called rain screen systems. And the way they work is that the exterior cladding is assumed to leak, and there is at least one other layer behind that cladding that acts as the water control layer. The cladding sheds water, the water control layer is the final line of defense. Of course, that also requires an air gap between the water control and the cladding somewhere. In many practical designs, there's more than one water control. There's the shedding layer, there's the air gap, the face of the insulation, then the water resistive barrier. We'll get into a bit more of that. However, don't forget 2 older strategies that we have used and continue to use. The oldest strategy is called the storage or mass approach, where we use that for thousands of years. If you have a thick enough wall of moisture tolerant and yet storing materials like brick or adobe, water does get past the outside surface, and that's known, but there's enough ability to store that moisture until sunny weather returns and the wall can dry out for this wall to perform adequately. The reason that there's been more emphasis in research and teaching about mass and storage walls in the last while is that not that we're building many of them, but we're renovating, retrofitting, upgrading thousands of buildings in our urban centers, converting old factories, and these types of buildings were based on the mass and storage approach to dealing with rain. The perfect walls approach, or the perfect barrier approach, or the exclusion is the principle, it's defined as having a layer where all the water is supposed to be managed. Now, that layer could be on the exterior-most face, or it could be a little ways in. The exterior-most face being the perfect barrier is called a face-sealed system, If the layer of water tightness is inward a little bit, we call that a concealed barrier. And this is widely used in our buildings. For example, most commercial low-slope roofs have an exposed, completely waterproof roof membrane that is intended by design to be the only layer that resists rainwater. And of course, almost every window or curtain wall or window wall uses the glass insulated glazing unit as the perfect barrier face sealed system. So we do use this a lot. Precast concrete's another one. So we often use in a modern new design the drained approach. And we look to the cladding to shed rainwater. We have a gap that drains water, and then we have a water resistive barrier as the final water control layer or the final barrier to water penetration. Of course, in a three-dimensional wall, we also need to have flashing to collect the rainwater and shed it to the outside. And to make sure that water can be shed by the water resistive barrier, we overlap stuff. Flashings are overlapped, sheets of membrane are overlapped, etc. So flashing is probably the most important part of any drained or rain screen system. This is where we actually switch from being a drained system to a perfect barrier system, actually. That membrane ends, and then we switch to some sort of metal or preformed plastic flashing. So the job of the flashing is to take water that's running vertically and direct it out of the building by turning it partly horizontally or wholly horizontally. So here you see in the photograph, it's clear they're trying to do that. They have a separate membrane. They're putting it down, making sure that the water can transition from flowing vertically to horizontally. Of course, we have to have weep holes in the cladding to allow this. And the challenge with flashings are either at the butt joints, and so that's why we like to seal them together in a way that can accommodate movement, but very much so at three-dimensional penetrations and details. So inside corners, outside corners. Here the bottom middle detail shows where a low wall, a parapet wall, runs into a higher wall. And that's quite a complex detail to get done right by flashing. And so here we have the type of detail you would purchase, a pre-made piece of metal or plastic that is sealed watertight like that, rather than expecting the trades to be able to build that in the field. Some of them it's impossible really to make a seamless joint in the field because the geometry of an outside corner, you simply can't stretch most materials that much. Now, the most common challenging spot for rainwater penetration and the most challenging spot for a drain system is the flashing under windows. So windows are placed in a rough opening which has variable dimensions. The window itself moves differently with thermal cycling than the wall around it. The window could often leak itself through hardware, butt joints, etc. And so the industry has learned that you've got to put flashing under those windows, and getting that flashing right is some of the best work you can do to avoid rain control problems in all systems, including drained walls. We show a number of examples here. You can buy membranes that you build on site into a three-dimensional construction. You can get stretchy membranes so that you have fewer joints. You can use fluid applied so that you can paint it on. And you can use preformed flashing systems so that the lap occurs at the simple spot here in the middle and at top where you can more easily seal them with simple tapes. So here's an example from the guide I mentioned earlier, page 36. There's a number of details showing how these types of ideas work their way into construction documents, or in this case, near construction documents. And you can see below the window, we have a flashing that laps and integrates with a membrane on the wall itself. We have an upturn at the back of that window flashing to make sure that water can't run in, or we need to seal it in a way that is watertight. And this is all about making sure we have continuity of the water and air control layer of the window to the membrane in the wall below. Now, we also have to worry about other things than just water. We also have to worry about thermal. And so we also have to make sure the thermal layers in the wall below line up with the thermal layer in the window. And the thermal layer in the window is always the gap, the gas fill or air fill between the two sheets of glass, or the thermal break, in aluminum systems. That's the thermal layer. It's got to line up and connect to the thermal layer on the wall below. So here's some flashing details. One of the things that we know about this flashing, and most flashings actually, is that water sits on them because, well, they're almost horizontal. And so when the water runs down the wall, it moves under the force of gravity. But after the water runs out, it'll always leave some puddles on horizontal surfaces. And so that water will sit there for quite some time. And as a consequence, it's recommended that the flashing under the window be made of a vapor impermeable material so that the water sitting on it can't diffuse through the membrane by vapor diffusion and wet the supporting structure below. So that's why we see here a vapor barrier type flashing under the window, and there's a vapor permeable type WRB, which is an air and water barrier. And here again, upper picture, air and water barrier is the white, and the blue is a vapor barrier as well as an air and water barrier. And the one above, you can see a very clear step in the flashing detail to use gravity to resist flow. This detail, these two will be using caulking as the way of stopping water from rolling backwards. Now, I mentioned these three-dimensional details earlier on, and they're very convenient because they speed construction, but more importantly, they give you reliable corners. And of course, these types of corners, these transitions, are exactly where you have the highest risk of workmanship failures. And so here's an example of a preformed window corner from the inside and the out, where the water and air barrier are wrapping into the window opening, and they're made continuous at this complex three-dimensional corner by a pre-manufactured but chemically compatible sort of three-dimensional detail. These are not expensive to buy, but they can really improve performance, and it's good not to overlook those opportunities when you have them. Another thing that's important in many drain systems is that you need a gap. It's not enough to have the membrane that stops water from moving further in the wall. You need to have a gap to allow water to drain to an exit. And the amount of water we're talking about is usually fairly modest. But you do need to get rid of it. And that means you need only a modest size gap. Even a 1/16 of an inch might do. But often we're using slightly larger ones, 1/4 inch or something like that. Now, these types of gaps are used for drainage and for ventilation of air. And we use them differently on roofs, walls, below grade, and below grade floors and slabs. And so I'll go through a couple of examples of each of them. And we'll start with the most common that people know, and that is a below grade air gap membrane, or dimple sheet is a way to call it. The purpose of the dimple sheet is to guarantee that when you backfill with local soil, you end up with a big enough air gap that water will drain down to the perimeter footing drain rather than build up pressure and leak into the building. Waterproofing is usually expensive and often more likely to fail than providing a guaranteed drainage gap. And by making a plastic sheet with dimples, you have a drainage gap. You can see the drain tile at the bottom in this photograph covered with stone. Stone is another way of providing drainage gaps. It's just that piles of stone with air gaps between them aren't always practical or inexpensive and can often fill up with silt. And so this is why people have invented these dimple sheets to guarantee that drainage gap below grade. When we use dimple sheets on the floor of a building, there's a different purpose. The primary purpose is no longer drainage, although it does perform that if you have a wet floor slab that water occasionally leaks up through. This will allow drainage to a perimeter drain or a central drain. But here the primary purpose is to be a vapor barrier that also allows water that might end up on a wet floor to laterally move through the air gaps that are formed by the, that dimple sheet. And it provides a little bit of insulation and gushiness, and so that allows you then put floor finishes on top. And this is where your air gap membrane is placed on top of the concrete slab. Now, this is clearly not the perfect wall, right? We wouldn't put the air gap and vapor and air barrier on the inside. But this is also a really powerful strategy for both retrofit and new buildings as a way of getting warm slabs that are dry, even though you're putting them over top of a ground contact concrete floor slab. Another example, this one a little bit more complex, is a dimple sheet where we put on the above grade wall. So this is a product that's sort of targeted at adhered veneer or stucco systems. Why those two? Because those are two systems where they store a lot of rainwater, and when they get heated by the sun, that water vapor can drive inward into the building enclosure and condense. And so you'd like to be able to intercept that water vapor with something that has low vapor permeance, e.g. a vapor barrier. And so this dimple sheet here is a vapor barrier, but it also provides the dimples needed to get drainage, so that rainwater that leaks through the stucco or through the adhered veneer will drain down and out through a flashing. And to allow the wall behind to dry out to the exterior, if that wall is made of wood framing, steel framing, or concrete, it has dimples on the back to provide an air ventilation gap. So a lot going on, drainage at the front, ventilation at the back, vapor barrier in between, all formed by a single roll of plastic dimple sheet. Now we go jump up to the roof, and we have a number of functions here. Primary one again is provide a drainage space for water that leaks through inevitably, metal roofing, ceramic tiles like terracotta, etc. It also separates sensitive metals like zinc and copper from the WRB. And so in this product here, it's actually an integrated water resistive barrier, air barrier, and this mesh that's not a dimple sheet, but it's a mesh that creates an air gap that lets air flow through it. It provides separation of the metal from the water sitting on top of that membrane. And it also performs a little bit of sound deadening, as they've discovered. It has become a feature. So for high-end roofs, in this case, in the left, you're looking at a zinc roof, not a cheap roof. This has become a pretty standard approach to ensuring the longevity and performance of that metal roof. Now, air tightness, that was rain control primarily and liquid water control. Well, now, next one down on the list is air tightness. And air tightness has become much more demanded in today's buildings. It's become aware that we need to have an air barrier system in essentially every building and every enclosure. And the reason we have more and more interest in air tightness, from policymakers, it's often driven by energy saving on a national level. Because air leakage does drive a lot of energy use in buildings, summer or winter. However, we actually have just as much of a demand to create air tightness to guarantee the air quality in the spaces we're in. And this guaranteed air quality comes because we now know where the air is coming from, because we controlled it. And we know what the quality is, because we get to run it through a filter. Air that accidentally leaks through your roof or the wall, A, is unreliable in terms of flow quantity and when it occurs, but it's incredibly unreliable as to its quality. It often just leaked through your wall or your roof, and so has mold spores and chemical off-gassings and pollen and other things that annoy occupants on the inside. And so this is why there's a real drive to not only providing an air barrier, but even testing the building to guarantee it as an air barrier before the building official will sign off. And this is happening in numerous North American jurisdictions. The requirement to test your building to prove it is certain air tightness. So to get an air barrier, we've known for years what's required. We need, again, something that's continuous. An airtight material is easy. An airtight system is dependent entirely on the quality of the connections, joints, and penetrations. We also need it to be strong enough to take the wind loads, because as soon as we provide a good air barrier, then we know that all the wind gusts will be taken by that air barrier membrane and have to be transferred to the structure. It has to be stiff enough that when those wind loads come, even everyday wind loads, it doesn't billow and flop around and fail by fatigue. It has to be durable enough. Depending where you put it in the building assembly, it might have to last as long as the entire building, because if, for example, you're putting it behind a limestone veneer in a museum, it has to last long enough that you're not going to take the limestone off to replace it. So you need to have a durable material. And of course, air impermeable. But that's pretty straightforward. Now, we have seen a change in the early days, in the 70s, especially in Canada, where air barriers started to be used in North America. The original approach was, let's take that interior vapor barrier we had and let's convert it also into an air barrier. And while that's practical and possible, it's a lot harder work, and we found it has many practical limitations. And so we started to get much better air tightness in buildings much more easily when we put the air barrier on the outside. And so it's easier to wrap the building on the outside because we have far fewer penetration, structural details, and connections that we have to deal with to make sure it remains airtight. So as an example of that, this is a simple 2-story steel frame building, but the number of holes and penetrations that would be left existing if I did wrap the inside of those steel studs with an air barrier should be obvious from here. Through the floor slabs, through the hollow core plank, at above ceiling joints, etc. There's massive air leakage, even if above on the steel stud I made a continuous board or membrane that was airtight. So exterior air barriers are often preferred, and also it turns out that, well, that's where we want to put our water control layer as well. We want to protect those steel studs, that structural steel, the wood, from getting wet. And so the obvious combination product is something that's watertight and airtight. Neither layer wants to have a hole in it. And yet, the way we deal with holes for water barriers is we can shingle up them. But for air barriers, they have to be mechanically or adhesively sealed. But once you've got them sealed for air tightness, they're pretty good for water tightness, of course. Now, if I put my air barrier / water barrier on the outside of my structure, but retain insulation inside between the stud frames, now I have to make that water air control layer be vapor permeable. We're not using the perfect wall approach there because the vapor barrier is either absent or on the inside. Now, 30, 40 years ago, that seemed like an impossible ask. Well, for the last few decades, product manufacturers have been around developing products that are watertight, are airtight, but are vapor permeable, making this exterior air barrier a completely practical approach to how one builds. So this is an example from a textbook of mine on high performance buildings, showing that sort of detail I showed with the photograph in what it would look like in a 2-dimensional, say, concept design or schematic design drawing. And by providing the exterior air barrier along the line of the sheathing, with a little bit of careful dimensions to start with, becomes very easy to build because there's none of those steel components of the floor slab, the open web steel joist, etc., penetrate through that air and water barrier. So it becomes much easier to achieve air tightness and water tightness. So you can't get an air barrier or a water barrier simply by buying a product that comes in sheets or rolls. You really have to get all of the continuity, and to do that, you have to have accessories that connect to other parts. This graphic shows that the obvious parts are, you've got the wall, you have windows or doors is the most common, and then you have to have a way of connecting them together. So to connect them together, we increasingly use tapes, again, because of advancements in technology. We use wet sealants, sometimes people call it caulk. We also use things like gaskets, rarely, because they don't always work that well. But we will use preformed components, sometimes made of flexible polymeric materials, sometimes made of stainless steel or copper, as a way of transitioning both 2- and 3-dimensional details that penetrate through the air barrier material itself. And so putting that together is the responsibility of the designer, and just show them in those design details. But we also now increasingly find families of products where the air barrier material has compatible accessories, including sealants and tapes and preformed components, to allow a designer to say, all of these things I know from the same manufacturer are compatible with each other, and I can build up all of the layers to get a continuous air and water control layer. So to get to good air tightness, one really does have to focus on those details, make sure we have continuity, and there are numerous air tightness targets that have been around for quite some time. One of the oldest in North America was the R2000 housing program that started in the early 1980s. Required blower door air tightness testing of every single home for certification. And that target they set at 1.5 total volumes of the house per hour when it was pressurized to a pretty high pressure of 50 pascals. Sweden was actually requiring in their building code air tightness numbers for every house of around 3 around the same time period. And over the years, we got better at air tightness, and we also started to apply these ideas to commercial industrial buildings. And we found that air tightness measured by air changes per hour was not a very good measure because we're really testing it per square foot or square meter of building enclosure. And large buildings have a different relationship of enclosure area to volume than do houses. And so to fairly compare the quality of the enclosure, we have been moving towards measuring things on a CFM per square foot, liters per second per square meter basis. And now, for example, people like the General Services Administration, U.S. Army, require air tightness testing and set targets based on CFM per square foot, not on air changes per hour. So how we design for air tightness is already I've said is that we provide an airtight layer, but then we connect all the details together in our design documents and make sure that practically we can connect them. Thinking about the construction sequencing, which trades are doing the work, and it often is helpful to do either mock-ups in the backyard of the architect, in the contractor yard, or at the start of construction, is to make sure that these layers fit together, there's enough dimensional tolerances, that they work in cold temperatures and warm temperatures, and that's how we make sure that the design ideas on paper can actually be built. And then we can move forward on that with a modicum of inspection to make sure that the ideas developed in the mock-up are actually delivered on all the details. So I mentioned here that fully adhered membranes are much more likely to work, and that's because when I provide a membrane for water or air tightness, if it's not fully adhered, it means that both water and air can flow behind that membrane. So any hole in the sheathing, air and water could flow behind it and find the other flaw some distance away in the membrane. When the membranes are stuck tight to the sheathing, the only way to get a leak of air and water is when there's a hole that lines up in the sheathing and the membrane at the same time. And those are easier to foresee in design, less likely to happen by accident on the construction site. Another risk is that because the wind oscillates, if that membrane is not held well tight to the wall, it can billow back and forth, and you still get airflow from indoors into the insulated cavity of the wall and then back out again, even though there may be no airflow between indoors and out. And the reason that air in your wall could be a problem is condensation in cold weather, air quality problems in any kind of weather. And so having a fully adhered air barrier or rigidly attached by some mechanical means is almost always a significant step up in performance. So this is an example of a parapet detail, a brick veneer wood stud wall connected to a exposed membrane wood roof. It's on page 51 of that tech guide. And there's a number of commentaries here about, it's not just to say this is the air control layer or this is the water control layer. It is about this is how the air control layer transitions from the wall to the roof or the roof to the wall. And so that's why we draw details. So basically the section of the wall design, you can just label the materials, but whenever you're doing a detail, it has to be clear how do we get that continuity of air, water, and vapor tightness. So accessories I mentioned are important. At the bottom right, you see a preformed window corner in place before the membrane. But you also see bottom left a flexible tape for around a circular pipe penetration. Next to that, you see a tape being used to seal around a flanged window in a residential construction site. Upper right, you see sealant, because we often will be using wet sealant as well to fill in gaps, and it's often the best choice. So you got to pick the best choice for the condition. So you'll see here, this is a building that has tapes and a membrane to connect them together, the pieces of sheet metal membrane to the windows, and also there are no penetrating roof overhangs or anything like that to ensure the highest likelihood of airtightness possible. Those overhangs were tacked on after the fact to allow us to have a continuous air barrier membrane, water barrier membrane, using tapes accessories to get a complete air barrier, fully adhered. Then we added some insulation and cladding on both inside and outside. So the last control layer I'm going to spend any time talking about is the thermal control layer. And the thermal control layer is almost always insulation, although an argon gap between two sheets of glass is also the thermal control layer. So we often live with quite a few holes, if you will, through our thermal control. But these holes aren't holes that are filled with air. These are holes filled with concrete or steel because they conduct so well. And so when we're looking at a building enclosure assembly, we're trying to look at one that has few holes caused by steel, concrete, and wood to a lesser degree through the thermal insulation layer. The building codes call this stuff CI, or continuous insulation, is by having a layer of insulation without steel or concrete going through it, we know that to be much more effective. Some of the common thermal bridges that bridge around insulation are things like concrete slabs, steel studs, both of which have an R value for their width, an 8-inch floor slab or a 1.5-inch steel stud of about R1. And that means that a lot of heat goes through those components. We also have windows and window frames in particular, which are lower R value and allow heat to leak out. So thermal bridges really can have a dramatic effect, especially on institutional and commercial construction, because this is where we use things like steel and concrete a lot. So a 6-inch steel stud with an R20 bat has an R value of about 5 as typically built, with double top plates, lintels, and double studs around windows. A wood stud wall gives you about R14 with the same kind of detailing. And that's because wood is not as bad an insulator as steel. And of course, windows have a pretty low R value, and so lots of windows, lots of reduction in heat flow control. If you look at various climate zones and standards, here's an example, ASHRAE 90.1, it will tell you a U value, which you then invert to get an R value. And that happens to be for what a climate zone, in this case 3. And you'll have a different number if you move to climate zone 5. But these R values are being stated in such a way that you're supposed to account for major thermal bridges. And so you have to know about those thermal short circuits. So speaking of thermal short circuits, it should be pretty clear that if each of those studs is R1 and each of those slabs is R1, that just putting insulation between the studs is not going to cut it anymore. Balconies, projecting slab edges are major sources of heat loss. And so we've had to move to putting insulation on the outside, not just between the insulation. Now, in the perfect wall concept, it's shown as all the insulation is outside the structure. But in practice, that's often expensive, and so we are coming up with hybrid walls where, yes, we fill up the stud space with some insulation, but we also put some on the outside to blunt those thermal bridges. This is an example of a system where you can see the air and water control layer on the outside, insulation, and limited amount of steel or plastic carrying the cladding load back to the support structure of the enclosure. So this is another plot from the High Performance Enclosures book, which tries to describe how if you have lots of windows, and that would be on the right of the bottom axis, 60% window to wall ratio, 80% window to wall ratio, depending on the quality of the window and the wall, you can see that your actual overall R value is quite a bit lower than what might be stated. These charts here say that really to get to a real R10, you pretty much have to use maybe 40% window to wall ratio or less, use high performance windows and pretty good walls. There's a whole bunch of combinations that are possible, but most of the buildings we're building today are down in this range here. And so the codes are moving us towards high performance, and what that means is an effective R value of only about 10 or so. But that would be triple what most building assemblies are today in commercial and institutional construction. So let's wrap all this up by summarizing what membranes do for us and how we can use them to provide the control layers. So the most common, and there are many products on the market, the most common combinations of products are water control only, air and water control, that is by definition vapor permeable, or air, water, and vapor control. So remember, we have those four control layers of air, rain, air, vapor, and heat. And normally when we buy that membrane, it's either the air, water, or vapor that is being controlled. So here's an example of one of the oldest control layers. I mean, it's been around for 100 years or more, and that is asphalt impregnated felt paper or tar paper. It is not an air barrier. It doesn't have the strength to be able to do that, and we don't have good techniques to seal the joints. But by doing merely gravity lapping, we actually can make quite an effective water control layer. Now, it's made of paper, and so one of the reasons it's being replaced is that paper is often sensitive to being ripped and torn, and also paper will eventually decay if you keep it wet all the time. So there's been a move towards more polymer-based products. So this is a vapor permeable membrane that's much stronger and fully adhered. And if you install it lapped with adhesive, this is a fully adhered self-adhesive sheet. You can get an air and water control layer that's quite vapor permeable. And so you can wrap it around window bucks as shown here in the bottom right, and allow those wet wood bucks to dry out, wet from construction moisture. And so now you have a polymer-based, stronger air and water control. And then we have what many people have seen, started to be on the market in the 80s and 90s, is the air, water, and vapor control. It's a little easier to make such a product because it's just a thick layer of asphalt or butyl, typically, with a facer of polyethylene or polypropylene plastic. And the facer holds that asphalt or butyl together, and it also allows you to stick things to the facer. So it comes in a whole bunch of colors based on the brand. And again, water control should be lapped, fully adhered, because these are sticky and self-adhering is always better than loose applied. And they allow you to put screws and stuff through them because they have enough gooiness that when the screw goes through, that there's not an obvious hole. Now, in the last decade, we've seen a whole bunch of fluid-applied products. And these fluid-applied products can be slathered onto the sheathing directly. But remember, you now don't have control of the thickness. So the tradesperson on the site now controls the thickness depending on how they put it on. The big advantage is that you don't have to make sure that they install the laps this way instead of this way. Because with the fluid applied, it becomes more monolithic, and you don't have to rely on trades to do this. But you do have to rely on trades to make it thick enough. And we still need to use membranes that are preformed to cross any large movement joint because you have to have something to apply the fluid to. And so rough openings of windows, etc. We have to think of wet sealants, peel and stick membranes, sheet metal, or something like that to transition over those gaps. So those details are critical to the performance, as I've stated many times, and you can't fluid apply over that gap, that 3-inch gap right there. You have to put a backer there. So in this case, they're using detailed sheets of self-adhered air, vapor, water barriers to transition to the body of the wall, which was a fluid applied, spray applied, asphaltic air, water, vapor barrier. What did we hopefully cover today, or do you understand? There are changes in the industry that have been building up pressure for the last few decades and are not getting less. And that means that we're seeing different products, different techniques of assembly, different codes and standards. The perfect wall concept primarily is one should be able to identify what's my water control, air control, vapor control, thermal control, interior finish, exterior finish, support. That needs to be identified on whether you're doing a precast concrete wall, a low slope roof, or a wood frame with exterior continuous insulation. That's the key to a good design. And then once those layers are identified, getting the details to stick together by drawing them to show that the water control on the roof connects to the water control on the wall, the air control of the curtain wall connects to the air control of the stud wall, is how we get that performance. So there are many variations that you can do to come up with literally hundreds and even thousands of practical, functional, and high-performance building enclosure assemblies. But in all cases, we're going to see continuous water and air control, which we always achieve primarily by good detailing and on the job site helped by good types of accessories from tapes and preformed flashings and caulking. So I hope this has been helpful, and I'm signing off.